All right, so on Wednesday, we covered spheres, right? And we talked about the two equations for spheres. There's no such thing as lateral area for a sphere because it's all one connected surface. So we said the total area was what? 4 pi r squared, and the volume? Good, 4/3 pi r cubed. So again, if you don't know those formulas already, my advice is spend at least a little bit of time over the weekend in addition to doing the assignment, which isn't that long. But I would also add on there some time to go through all these formulas. So one just says find the surface area and the volume of the sphere if the radius is 6. So surface area or total area would be 4 times pi times 6 squared, 4 times pi times 36. And I got 144 pi, this is feet squared. And then volume. Volume would be 4/3 pi 6 cubed, 4/3 pi times 216. 3 goes into 216 72 times. And then 288 pi feet. This time it's cubed. Questions so far? Okay, so on your test, you'll do the same thing. You'll leave it in terms of pi. You won't have a calculator, so there'll be numbers that you can deal with without it. As far as the pyramids and stuff like that, if you've got a root in your answer, you'll keep the root in your answer. And then if it's pi, you'll keep pi in your answer. All right, surface area and volume of the sphere. Now you're given that the diameter is 12.4. So what happens if I have to cut this in half? 6.2, that's my radius. So 4 times pi times 6.2 squared. 6.2 times 6.2. And then that would get decimal moved 2 places. 4 times pi times 38.44. Multiply that times 4. Move my decimal twice again. So 153.76 pi meters squared. And then volume. So 4/3 pi 6.2 cubed. So I already multiplied 6.2 times 6.2 to get the 38.44. I'd have to do it again. 6.2. And move my decimal 1, 2, 3 places. So it'd be 4/3 times pi times 238.328. Don't worry, we're not going to do this to you on your test. And then if that's divisible by 3, which I don't know if it is, I would divide it by 3. Let me see if it is. All right, so it's not divisible by 3, so I'm going to multiply it times 4, so 238. All right, so I did 4 times 238.328, and you should have gotten 953.312 over 3 pi and meters cubed. All right, 3 says the great circle of a sphere has a circumference of 16 pi inches. Find the volume of the sphere. So remember, the great circle would be as if there was a sphere and I went all the way around the center there. So what it's telling you is that the circumference of this is 16 pi. So what does that help you with? It tells me I can work backward to find the radius, right? I can go diameter and then cut it in half, find the radius, doesn't matter. So this is 2 pi r. Divide by 2, I get 8 pi equals pi r. Divide by pi, and I get that r is 8. And then volume is just 4/3 pi 8 cubed. So 8 cubed, 512. 5 plus 1 is 6, plus 2 is 8, not divisible by 3, so I'm going to multiply the 4 times it. And I would leave it over 3 inches cubed. Questions on that one? Alexis?
Is it just that, like, the numerator and the top number that's times pi, or do you put it, like, off to the side?
It doesn't matter if you put it with the top or with the side, it's the same thing. As long as you don't put it in the bottom, it doesn't matter. All right, find the radius of a sphere with a volume of 4,445.18. So obviously this is one that you won't see those kind of numbers on your test, because this I would say you would use a calculator for. So if 4/3 pi r cubed equals 4,445.18, probably first thing I would do is multiply both sides by 3. Get rid of that. So 4,418 times 3 gives me that 4 pi r cubed equals 13,335.54. Divide that by 4. And I get r cubed equals 3,333.885. And then the cube root of that. Oh, sorry, got to divide by pi. There's still a pi. So 3,333.885 divided by pi is 1,061.208, and so on and so forth. So cube root of that gives me 10.2. And this would be in feet. Question so far? All right, so that was, there's one more, right? Yeah. Find the surface area and the volume of the solid. So this is similar. We did one in the examples the other day in which there was a cone on top, right? Or I mean, that shape like an ice cream cone with the bottom being a cone. Now I've got that same shape on the top, which is called what? What's half a circle called? Hemisphere. The hemisphere. So this is a hemisphere over a cylinder. So if I want to find the surface area and the volume should be easy. Find the volume of one, add it to the volume of the other, right? That should be the easy part. What's different about surface area here?
You have to.
Oh, it's like this one.
You have to only find the bottom, like half of the circle or the sphere.
So the sphere, I would find half the surface area, right? Because I just take off that half. What do I have to do with the cylinder?
You have to. You can't like do the top part.
Good. I have to take away a base, right? So when I do 2b plus lateral area for my typical surface area of that cylinder, I take off the 2 and just do b plus lateral area. Does that make sense? Okay. So let's do that work.
Well, why do you have to, like, why can't you just find the surface area?
So the surface area of the bottom, so if you just add the 2 together, you're including the surface area of the top of this as well, as if you could cover that. And there's not. This is one fluid shape that wouldn't have that part. Does that make sense? Yeah. So volume doesn't matter because you're doing the hemisphere on top of it. You're going to fill both of them. But the surface area, you've got 2 sections that overlap that you can't account for. So let's do the volume first, since we said that was easy. Volume of the hemisphere plus the volume of the cylinder. So the volume of the hemisphere would be 1/2 the volume of that sphere. So 4/3 pi 4 cubed. 1/2. 4/3 pi times 64. 256 over 3 times 1/2. This is 1, 2, 8. So 128 pi over 3 is the volume of the hemisphere. Yep.
Like when you're finding the volume of a hemisphere, can you just do 2 over 3?
Sure. Yeah, you can do the 1/2 times that 4/3. It's the same thing. Then volume of the cylinder. So the cylinder, how do I find the volume of the cylinder? Good. Pi r squared times height. Remember, it's just like a prism, right? Which would be the base area times the height, except the base is a circle. So this would be pi 4 squared times 4, pi 16 times 4, pi times 64. So to find the volume of the entire shape, I'm going to add these two together. They both have a pi, so I can actually take this a step further. I just have to find the least common denominator. So if this is over 1 and I want to get it over 3, I'd have to multiply this by 3. And I'd get 128 pi plus 192 pi over 3. What was the units on this? Meters. Questions so far? So volume, take the volume at the top, which is the hemisphere, volume at the bottom, and add them together. Okay, but then we said when we go to find the surface area, we can find the surface area of a sphere and cut it in half, because that's exactly what we're looking at for the top. So half the 4 pi r squared, which is what Evan's question was. Can I then take half of this? And yes, you can, because that's the same thing. This would be 2 times pi times 4 squared. 2 times pi times 16, 32 pi is the surface area of the hemisphere. And then I have to add that to the surface area of the cylinder with only one base. So it's going to be pi r squared instead of 2 pi r squared plus pi r h. Plus 2 pi r h. Because that would be lateral area. So pi 4 squared plus 2 pi 4 times 4. There's a whole lot of 4's in this. 2, this is 16, this is 32 pi 8. So I take these two and add them together. And it's area, so it's meters cubed. How many meters squared? Fernando. So the 128 over 3 came from, the 128 over 3 came from the half the volume of the top, or half the volume of the sphere, which would make up the top. Yeah, so the hemisphere. And then the 192, I just changed it so that the 64 pi had the same denominator. I gave this like 64 pi over 1, changed it so it had the denominator of 3, so I could combine them together. Ninth and final section in this chapter. It's a long one, especially if you consider that we added in total area, which is why we divided this chapter into 2 for your test. So your test will cover technically sections 6 through 9, adding in the total areas that we did of prisms, pyramids, cylinders, and cones. So 11.9 is exploring similar solids. Similar solids are solids of the same type. So 2 cylinders, 2 cones, 2 rectangular prisms, 2 square pyramids with equal ratios of corresponding linear measures such as heights or radii. So linear would be measurements that when we find the units of, we never square. So length would be linear, radius would be linear, perimeter is even linear. If you remember similar triangles and similar polygons, we had a scale factor, right? Scale factor is the ratio of those measurements. So if I have 2 similar, cylinders, and the ratio, and the radius of one is 2 and the radius of the other is 3, then my scale factor is 2 to 3. Because all the sides are the same on a cube, every cube is similar to another cube, okay? They're not congruent. I can have a teeny tiny cube and a big huge cube, but they are similar. And then any two spheres are also similar because of the same reason. You only have one linear measurement on a sphere. And it's the same all the way around. All right, so theorem 1113 is the similar solids theorem, and it says if two similar solids have a scale factor of a to b, whatever those numbers are, then the corresponding areas have a ratio of a squared to b squared. And the corresponding volumes have a ratio of a cubed to b cubed. All right, so example 1. Question 1, are all spheres similar? We just said this. What's the answer? Yes. Are all right cylinders similar? No, their radiuses might be in the same ratio, but their heights, right? You could have a short cylinder that has a radius of 3, and you could have a tall cylinder that has a radius of 3. Those would not be similar. How about all cubes? We just said that one too. Good. If I were to take a cylinder, right, that has, let's say that the radius is 3 and the height is 4. And then I have another cylinder and the radius is 6 and the height is 8. So the ratio there is the same, right? Whether I go 3 to 6 and 4 to 8, each of those would be 1/2. Or I did 3 to 4 and 6 to 8, it would still reduce to be the same. These would be similar, okay? Whether they were oblique or right, it doesn't matter. It's do their measurements measure up, okay? But if I had one that was 6 and 5, now these are not similar. Does that make sense?
Yes.
Okay. All right, two cones have a base radii of 8 centimeters and 12 centimeters and heights 16 centimeters and 24 centimeters respectively. Are the cones similar? So you can give yourself a visual, and a lot of these times you might not even need to, okay? I've got two cones. It says this one, radii of 8, radii of 12, and then this one, height of 16, height of 24. So I can either go radii to radii, height to height. I could say 8 to 12 has to equal 16 to 24. Or I could go radii to height and radii to height. If these reduce to be the same, then they're similar, and if they don't, then they're not. So if I did the first one, how does 8 over 12 reduce? No, 8 over 12. The one on the right, the first one I did. How does 8 over 12 reduce? 2/3. How about 16 over 24? 2/3. Okay, what if I had set this up? 8 over 16 and 12 over 24? 1/2.
So what if you did 8 to 24 and 12 to 6?
So that you can't. You have to match the measurement with its same measurement. So radii has to go to radii, height has to go to height. Or within the triangle, you have to follow the same pattern. Radii to, within the cone. Radii to height, radii to height. Does that make sense?
So how do you know which one goes with which?
Radii will go with radii. Height will go with height. So the word respectively tells you the order here. This goes with the first. This goes with the second. So respective means follow the same order we already established. So, but if it asks what the scale factor is, so this is important because to establish whether or not they're similar, it doesn't matter if I use the first method or the second method. But if it asks what the scale factor is, I have to use this first method. I have to use radii to radii and height to height. So the scale factor of these would be 2 to 3. Does that make sense? And again, with scale factor, it usually gives you an order, like what's the scale factor of the smaller to the larger, and that way you know you have to separate it out. Alexis.
I know that like the question is say like
No, yeah, no, you're just going to use the theorem. Yeah, you don't have to justify this. You just have to. And go a step further with this. So if we know that the scale factor is 2 to 3, what's the ratio of the perimeters? 2 to 3. So scale factor is a linear measurement, so it's perimeters, right? Those would be the same. How about what's the scale factor, or what's the ratio of the areas? So if this is A to B, good. Then I square it and I'd get 4 to 9. How about volumes? 8 to 27. So I take the original scale factor and cube it. Does that make sense? So linear is A to B, area is A squared to B squared, and volumes A cubed to B cubed. All right, two similar square pyramids have base areas of 4 meters squared and 36 meters squared. Find the ratio of the heights of the pyramids. And then if the height of the regular pyramid is 27, what's the height of the smaller pyramid? So actually, let me go back to this. Okay, so now back to this one. This time it gives me the areas and it wants the ratio of the heights. So if I've got the areas, how do I work my way back to the heights? Good. So if this is my A squared to B squared, and I want to go back to the A to B, then I just square root both these measurements, and that would be 2 over 6. Okay? Do you always reduce a ratio? Yes. So what would that really be? 1 over 3. And then B says if the height of the larger pyramid is 27, what's the height of the smaller pyramid? So what ratio would I do if it's heights? I just said it's 1 to 3, right? And it's telling me the height of the larger one. Is the larger in the top or is the larger in the bottom? Good. So I'm trying to find the height of the smaller one. So this one hopefully is pretty easy. Like I can go straight across, right? 3 times what gives me 27? 9. So I can do the same thing up here. But if it wasn't as obvious, then I would cross multiply and divide. What if I had given you the ratio of the volumes up here? What if I said the ratio of the volumes? Good. So because you had asked about this, Alejandro, let me go back to that one. So let's say it's 81 to 64. So this would be A cubed to B cubed, let's say, 81 to 64. To work my way back to A, I want to cube root 81. So sometimes they're going to be obvious and maybe ones you know. And that's a really bad example because that's not one. This needs to be 27. Actually, let me work it out like it isn't. Show you what happened. Okay? So if it's a perfect cube, then when I break it down, let me do that on the bottom first. This would be 4 and 16, which is 4 and 4. If it's a perfect cube, then you're going to get exactly 3 of that number, right? And the cube root of 64 would be 4. If it's not a perfect cube, so 81 is, let's say it's 9 and 9, 3 and 3, 3 and 3. Do I have exactly 3 3s? No. So the 3 that I do have a triplet of, those 3 go to the outside of the cube root, and the 1 3 stays underneath.
But are they still similar?
Yeah, this would like the directions here would say the ratio of two similar solids have volumes of 81 and 64. What are the ratio of the side lengths, the perimeter, the radii, the height, any of that? And it would be 3 root 3 over 4.
So then the little 3 is like...
The cube root instead of it being square root. Evan.
You have to